Okay, so now what do I do for the rates? Do I have everything I need there? At least at this concentration I do. I mean, at this first point I do, because the initial concentrations are given. So let's go ahead and put those in. So the rate of A is equal to negative K1 A times the concentration of A minus K2A times concentration of A squared. All right, so we get that. And then RB is equal to positive K1A times concentration of A. And then RC is equal to positive K2A times concentration of A squared. That's why I made the concentrations their own thing, so that I don't have to keep typing the concentration terms into here. Especially because the concentration terms are actually going to get more complicated once we leave this initial point. All right, so those are our initial rates. We're going to put in another, I don't like not having units, so liters, moles per liters, moles per second per liter, moles per second. Liters per mole second. Okay, so now what do I do for the second row for the volume? The initial, it's the previous volume, not the initial, sorry, plus delta V. And of course, we got to make this not change. What about the initial concentration, or what about the concentration? I mean, we put them under stoichiometry. The mass balance part is how we're going to do the flow rates. Those are the material balance equations. So the stoichiometry just says take the total concentration, or sorry, the total inlet concentration. So we can come back over here, and even though it's the same, just to avoid any confusion, we're going to put total inlet concentration, and again, it's the same. And so the formula that we wrote down was total concentration times the flow rate of A divided by the total flow rate. So that's the flow rate of A divided by the sum of the three flow rates. And of course, that's not there yet, so I'm going to get a divide by zero error. It's not a big deal. It'll be there in a second. Times T naught divided by T. And again, the temperature's not there yet. So anything in P is what we're fixing so it doesn't move. And actually, if we fix the sum, if we fix the columns on the sum, we can save 2 seconds. There we go. Ah, damn it. I need to fix the columns on temperature too. All right, so again, a bunch of nastiness right now. What about the rates? Have those formulas changed from the previous cells? No, so we can just drag those down. Obviously, it's not going to work right now because the concentrations are all screwed up. What about the flow rates? So what do we put there? That's the differential part, right? So here's where we use the Euler method. And so what we're doing here is it's the previous flow rate plus delta V times the right-hand side of the differential equation, which is what? RA. If we don't know RA, we get a circular reference. If we chose this one, that's why we choose the previous one. So now you see that the flow has dropped a very small amount. Does that make sense to everybody? Good. And now I can put my dollar signs in, and then I can just drag this over. And both of these flow rates have gone up by a very small amount. All right, what do I do for temperature? That's the energy balance equation, which is also differential. And this one's kind of big, so just bear with me while I type it all in. It's going to be the previous temperature plus delta V times, we've got a few things here, UA times the ambient temperature, or the temperature of the cooling fluid, minus the temperature that I'm at. And so again, I don't know the temperature I'm at within this one, so that's why I use the previous temperature plus minus R1A, which I wrote down previously. That's just K1A times CA. Times -1 times delta H reaction of 1, the first reaction, plus now the same thing but minus R2A, which I also wrote down, that's K2A times CA squared, times -1 times the delta H reaction for that reaction. All right. And then what's in the denominator? Flow rate times the heat capacity plus the flow rate times the heat capacity, et cetera, et cetera. There actually is a useful formula here, but I'm not going to use it, called sum product. But anyway, it's just 3 things. If it was more, I'd probably use it. That's it. The temperature goes up a little bit. Does that make you feel warm and cuddly inside?
Yes.
Yeah, 2 exothermic reactions should go up. Now, of course, maybe not, because the cooling fluid is at a colder temperature than your inlet. So maybe if you're removing more heat than you're generating to start, that could go down. But it doesn't. I solved this problem. It goes up. Do these change at all? No. Okay.
Oh, the formulas don't change.
The formulas don't change.
Okay.
Yeah, sorry. Otherwise, we wouldn't even have them in a column. So I dragged this down 500 cells. And I think in this one, some of the, don't be thrown because some of the columns are not in the same order. But anyway, this is what we get. So I drag it down 500 cells. That's going to give me a total volume of, I think, 10 liters. We'll check real quick. 1 liter, sorry. 1 liter. And so let's look at some of these profiles. I've also added on here some of these selectivity parameters. So selectivity, I put here overall selectivity as SOV because I don't know how to do the hat thing in Excel. And then yield, and then overall yield of B. So first, what happens to the temperature? Increases, hits a maximum around ½ of a liter at little over 800 Kelvin, and then starts to decrease. Does that make sense to everybody? Hmm?
Does it run out of A? Like,
Does it run out of, say that again?
never mind.
Why does it decrease in this region? Yeah, and so you can kind of tell that because it's a straight line. There's 2 reasons why the temperature can go down, right? It either means that you're removing heat faster than you're generating it, which that's the only reason, I should say.
Or the reaction.
But what if you're not generating any? Then the heat of removal is just going to be a straight line. So if you see a flat, a straight region in that plot, that should be a hint to you that the reaction's already at 100% conversion by the time you get there. So when the reaction's taking place, we're always heating, right? There's never any moment where the amount of heat removed from the system is greater than the amount of heat generated until the reaction stops. And again, you can tell that by looking at this plot. Remember, this is a parallel reaction, not series. So you wouldn't expect that these would decrease as you get to a larger and larger volume. And so at around the same liters, right, around the same size, all the A is gone from the system. And which is which? You actually can't just know off the top of your head. Let me pull it up. Yeah. This is the flow rate of B. This is the flow rate of C.
You know that though, because B is going to get.
You don't know the rate constants. I mean, you might if you're like a whiz kid and you did the math in your head, but yeah, I wouldn't expect you to know the. But no, this is B, orange is B, gray is C. Okay? And B is the desired species in this system, so we're going to come back to these, but first let's look at now I want to look at, what do I want to look at? instantaneous. All right, let's look at the overall selectivity for the system. So this is the flow rate of B divided by the flow rate of C. So pretty good, right? Around 15 or maybe 30, closer to 30. It drops, and then it hits a constant value of 2.5. Why is it constant?
A is gone.
Because the reactions are done. Right, so again, that big flat region tells you that you're not doing anything anymore. What happens if I look at the instantaneous selectivity? That's this blue curve. So again, it decreases, and there is a small region where you're actually, at that moment, making more C than B. But for the most part, the instantaneous selectivity is greater than 1. And then you see it just starts to shoot up and up and up. What's happening there, and why doesn't it affect the orange curve?
Which again?
The blue curve is the instantaneous selectivity, which is the rate of production of B divided by the rate of production of C. The orange curve is the flow rate of B divided by the flow rate of C at that point.
If it's going to infinity, it just means the rate of production of B is much higher than the rate of production of C. So
That's true. So the rate of production of B is way, way, way higher than the rate of production of C. At the end of the reactor, it's over 10 million or something. But why doesn't it affect the orange curve?
You need 2 A's for a C.
Say that
You
again?
need 2 A's for a C.
You need any A to do any of this.
Right, but that's the thing is that if there is any A left, it would go to B much more quickly than it would go to A.
So you're kind of answering why it goes up.
Yeah.
And you're right. It's because as A gets very, very small, because the unselective reaction requires 2 A's, it occurs at a rate proportional to the concentration of A squared.
Yeah.
So the denominator for this term is concentration of, or rate constant times concentration of A squared. The numerator is a rate constant times concentration of A. So if you write out and you solve for the instantaneous selectivity, what you'll see is that you're inversely proportional to the concentration of A. And that